work, just a type of energy. Let's talk about another type of energy, and that is kinetic energy. All right? Kinetic energy is the energy associated with motion. Gesundheit. So I'll say it's the energy associated with a moving object. And let's just jump right into the definition. Kinetic energy is equal to 1/2 times the mass of the object times its speed squared. 1/2 mv squared. All right? If I look at the units of kinetic energy, what do you think they should be? Should be joules. All right, it's energy, so it should be joules. So units of energy are equal to the units of mass times the units of velocity squared. So kilogram meter squared per second squared is what I get, which again is just a Newton meter, which is just a joule. Okay, so I am consistent, I'm not cheating. A few typical values for kinetic energy. Of a few different objects. So let me preface this by asking you, you have a bullet, you have a fastball, it's probably just one word, and you have a running dog. All right, a bullet moving at typical bullet speeds, a fastball moving at typical fastball speeds, and a running dog moving at typical running, let me spell running right, running dog speeds. So what do you think has the largest kinetic energy associated with it? So a bullet, very small mass, fastball, sort of middle mass, running dog, bigger mass, bullet, bigger velocity, fastball, moderate velocity, dog, kind of slowish. All right, so you can do the calculation. If you say the bullet, for typical values of a bullet, in my head it was something like 8 grams, so really light. But a bullet moves at typical speeds are about 400 meters per second. So you get a value of something like 750 joules. A fastball moving at 95 miles per hour with a mass of like a quarter of a kilogram, you get values of, what do they calculate, 100 joules. And a running dog, I don't know, 30 kilograms, moving at about 5 meters per second, you get something like 375 joules. All right, so yeah, the bullet, even though it's really light, velocity sort of, speed matters more because we're squaring the speed. All right, we're squaring the speed so you get sort of double impact from the speed. So the light object has more kinetic energy in this example. All right, so kinetic energy is very easy to calculate. You're given a mass, a speed. Kinetic energy is just 1/2 mass times speed squared. Nothing really tricky there. It's just another form of energy. The way that we make things tricky in physics is through a statement. So the statement goes like this. If an object that has some initial kinetic energy at some initial time has a different amount of kinetic energy at a later time, in other words, if the kinetic energy of an object changes, then there must have been work done by some force. All right. So this is a line that's very similar to what will be written in your book. And this is very accurate when we're talking about mechanics, which is, of course, what this class is all about. We generalize this a little bit more as we get into other types of physics, but for all intents and purposes, this is exactly true. I like to state this in a slightly different way. I like to say if the kinetic energy of an object changes, then there must have been some other energy added or taken away. All right? So if kinetic energy changes, then energy in some form must have been added or taken away. All right, this statement in itself is actually really, 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 really important. This is probably the most important statement that I've said in this class so far. Another way to say it is that energy, and you've probably heard this before, cannot be created or destroyed. And the next two chapters are sort of devoted to solving problems where energy is transferred from one form to another, but it doesn't just magically disappear. And that's why I start off this section by talking about work and how it's actually just energy. Okay, because you can relate work to kinetic energy and all the different forms of energy, and you can change energy between one form and another as long as it doesn't just magically disappear. It has to go somewhere. All right? This is one of the most important statements I'll make in this course, and we use this idea in very complex ways in all sorts of different areas of physics. And so the next step is to talk about what textbooks generally refer to as the Work-Energy Theorem. All right, in its simplest form, the Work-Energy Theorem says this: the work done is equal to the change in kinetic energy. Okay, now I want to point out this is the network done by all forces acting on an object. Acting on, there we go, an object. And this really, this pretty much says what I just said. I just said that energy can't be created or destroyed. If we change the kinetic energy in an object, then you must have work done. Now, work in this case is done by all forces acting on an object. That could be, what have we met so far? We haven't met any other, we haven't talked about any other sources of energy in any detail, or any other types of energy in any detail. But that could be work done by the gravitational force. It could be work done by me pushing. It could be work done by a frictional force. It could be work done by a spring, etc. All right? And this pretty much states what I just said previously, with the exception of it doesn't really account for heat. So it kind of does, but it kind of doesn't. So we're really just applying this in mechanics, which is, again, what this course is all about, what we've studied so far. So pretty much this is an okay thing to say. If you have a change in kinetic energy, in other words, if an object speeds up, it doesn't change mass, it goes faster, energy must have been added by some force. That's all that this says. And we can calculate the energy done by calculating the work done by that force. All right, now I said net work done. So in order to calculate the net work, I have to take into account each force. And in this case, each force individually can be doing positive work, can be doing negative work, or it could be doing zero work. It just depends on the force and how it relates to the direction of motion and things like that. All right? So like I said at the beginning when we were first talking about work, how you could talk about the work of an individual force, you could talk about the work done by all the forces. That's what this is, the network. Okay? And each of those individual forces, they could be doing negative work, in other words, adding energy to the system, or they could be doing negative work, positive work and taking energy out of the system. They could be doing no work at all. And it just depends on the force and how it relates to the motion of the object. All right, so this is the work-energy theorem in all its glory for you to have and behold. Let's actually get to applying this sort of thing now. All right, so we're going to go to the text tool here, and we're going to have a car. So there's a car and the driver of the 1,000 kilogram car that is moving at a speed of 35 meters per second. Slams on his brakes, which apply a force of 8,000 newtons to the car in order to make it stop. The question I have is at what minimum distance should the brakes be applied in order to avoid a collision? All right, you've got a car, it's moving, it's getting close to another car, you can think of that, and you want to hit the brakes, you just want to know when. You like to get as close as possible to the car in front of you. All right, so here's the car, it's some distance d away from another car. We're trying to find that distance. The motion is in this direction, so that's the v, the velocity v. The frictional force acting on the car is pointing in that direction. All right, so even before I start the problem, I'm asking about the distance the brakes should be the distance the brakes should be applied. I'm asking about that distance, but what do I know about the work done by friction? So friction is going to do some work in order to change the kinetic energy of the car. The initial energy of the car here is some value. It has some kinetic energy because it's moving. Later on, we want it to stop. In order for the kinetic energy to change, work must be done by the frictional force. What can I say about the work done by the frictional force? Is it positive or negative? Or zero? All right, it's negative. All right? I know it's negative because the frictional force is applying opposite to the direction of motion. So my work-energy theorem states that the work done by an external force is equal to the change in kinetic energy. So kinetic energy final minus the kinetic energy initial. In other words, work done is equal to 1/2 mv final squared minus 1/2 mv initial squared. In this problem, the mass is the same. The mass of the car doesn't change. That doesn't have to be the case. So, just keep in mind, a lot of the problems, a lot of the examples we'll do, the mass is the same because we're just considering one object. But be careful. If you're doing a homework problem, as we go forward, the mass may in fact change. Initially, we're moving with some velocity. It's 35 meters per second, but we're asking how far do we have to go before we can stop? All right, so this term right here is 0 because the final velocity is 0. So that tells me right off that, yeah, my work is going to be negative. It's going to be 1/2 mv squared in the negative direction, or with a negative sign in front of it. So I'm happy there. I can calculate the value of that work. So you go to negative 1/2 times the mass, which is 1,000 kilos, times the speed squared, which is 35 meters per second squared. And I get a value of negative 6.13 times 10 to the 6th joules. All All right, that's how much energy is required to stop the car. Now, before we go on, let me talk about this value. It's negative, which means that what I said before is if you have a negative work, you're putting energy into the system. Does that make sense with this picture? What is the system? What am I referring to when I say the system? Shooks? You pointed and you said something. What do you think? All right, it's not the car's displacement. That's not really the system. The displacement isn't a system. Okay, it's a good guess though. That's sort of I think that's one of the obvious choices. What else? Derek? So I'm putting energy I'm giving energy to the brakes basically. The system is the car or the brakes. So I'm giving the system energy. So if you think about, well, wait, if I'm giving the system energy, shouldn't I be like speeding up the car or something? No. So where is that energy really going? Friction and then heat. All right, so that energy is being given to the brakes in the form of heat. So I'm adding heat to the system. When you have friction, two things rubbing together, that creates heat. So again, energy isn't being lost to nothing. It's not being destroyed. It's being transferred to the brakes and then turned into heat. And that's where that energy goes. It's dissipated in the form of heat, and then also, if you use your car a lot, you have to change the brake pads. Why? Because the brake pads, they go away. You lose all that material, so it goes into the energy of the particles that are being thrown out from your brake pads. Okay, so that's where the energy is going. All right, but back to the problem at hand. So this is how much work was done by the brakes. I'm trying to find this distance. Well, I know that work, in addition to being equal to the change in kinetic energy, the work done by the frictional force is equal to the force dotted with the displacement. All right, so I can solve this. I can say that, all right, well, I know that that's actually the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. The angle between the force and the displacement is 180 degrees, so this is actually a -1. So if I calculate the work done, it's going to be equal to the negative of the force times the distance. But I just solved for that. That's up here, so that's actually equal to -613 times 10 to the 6th joules, which tells me that my force is going to be equal to my distance, thanks. Distance is going to be equal to -6.13 divided by -f. In other words, the negatives cancel out. So I get 6.13 times 10 to the 6 joules divided by the force, which I said to be, what did I say the force was? 8,000. 8,000 newtons. And the answer that you should get is 76.6 meters. So that's the minimum distance that I need in order to avoid a collision. I was being extremely thorough here, including the negative signs, so I had these negative signs kind of cancel, and that confirmed that my displacement was in the positive direction. All right, so this is actually a vector, it's in the positive direction. I want to write it as a vector. So the distance is to the right. No, work will not be on the exam. Yeah?
How come in this example we use an angle of 180 degrees and in the first example we use an angle of 0 degrees?
So in this case, when I was calculating, that's a good question. So in this case, the displacement, D, is this way.
Yeah.
The force of friction is pointing this way.
Okay.
So the angle between those, which is like that, is 180 degrees.
Okay.
No problem. Yeah, Derek?
So just to check, following. So what we did was we solved the Work-Energy Theorem, and then we inserted that into the definition of what we solved as displacement.
Yeah, so we sort of have two definitions for work. We have work is equal to the change in kinetic energy, but it's also equal to a force over a distance. So we just solved sort of both of those, and we were able to get distance out. So basically what this says is work which is force times distance times cosine theta, is equal to the change in kinetic energy. So that's what we solved. Danielle, did you have your hand up?
Yeah, why wouldn't you make the force of friction negative?
Why wouldn't I make the force of friction?
I know it wouldn't really make sense because then you're just
Because this is a all right, so I sort of did, but that's because this is a magnitude. So I just take the number and then the direction comes into play here. Okay. Other questions? All good questions. Nope. All right, cool. We're going to extend this question a little bit. So I'm going to ask as an extension, so if we apply the brakes at 30 meters from the car, so from the car that we're about to collide with, I want to know what is the speed of the collision. All right. So again, you're going to apply the work-energy theorem. We have a distance of 30 meters. We have a force of 8,000 newtons, and initial speed is of 35 meters per second. All right, so we have this is a classic work-energy theorem. So I'm going to write down the work-energy theorem, which says that the work is equal to the final kinetic energy minus the initial kinetic energy. All right, since I'm looking for a distance here, that's not the distance. That is the distance. I have a distance, so I have a distance here. I have a force. I know that I can solve for the work due to the friction. So that's going to be equal to the magnitude of the force times the magnitude of the distance times the cosine of the angle between them. That's equal to the final kinetic energy, which is 1/2 mv final squared, minus the initial, which is 1/2 mv initial squared. All right? This is the equation I'm solving, and I'm solving it for the final energy, or the final velocity. All right? And I know everything in this equation. Okay, so the first thing I know is that the cosine of theta, the theta in this picture, I have a displacement in this direction. My force applies in that direction, just like our previous example. That's 180. So cosine of theta is -1. So what I have here really is I have a negative magnitude of my force times the magnitude of my displacement is equal to 1/2 mv final squared minus 1/2 mv initial squared. Notice I tend to solve things in terms of letters, and I had this discussion with a few people before class. I like to solve things in terms of letters because I think it's easier to catch my mistakes and then plug the numbers in later on. It's a little bit easier to follow when I'm looking at letters as opposed to numbers because the numbers tend to be a lot longer than the letters. So that's why I do it this way. You guys may have put numbers in earlier. You may have solved for the work, which is fine. I'm just going to solve it outright like this. All right, so what I'm after is the final velocity. So I'm going to put that over here. 1/2 mv final squared is equal to the 1/2 mv initial squared minus force times distance. So my v final has got to be equal to, I move the 2 to the other side, and I get the 2 cancels out here. The mass cancels out there, so I get v initial squared minus force times distance times 2 divided by mass, and then I got to square root that whole thing. All right, now I'll plug in some numbers. Initial velocity was 35 meters per second. Meters per second, and I'm squaring that. My force is 8,000 newtons. My distance is 30 meters. My 2 is 2. And my mass is 1,000 kilograms. All right, and if you solve that, if you run that through your calculator, you will get, in fact, 27.3 joules. Not joules, I'm sorry, not joules. Meters per second, sorry. And you can check your units to make sure they work out. Obviously, this first term is going to be meters per second squared. Square root of that is meters per second. It's a little bit harder to see over here. Newton is a kilogram meter per second squared, so my kilograms cancel out right here. And then I'm going to have a meter times a meter, which is a meter squared, divided by a second squared. Again, square root gives me meters per second. So I'm happy with my units.